Stanford University.
Welcome to the seminar on People, Computers, and Design. I'm Terry Winograd. Quick announcement. Next week we have two designers, Michael Magursky and Tom Carden, from a company called Stamen Design, who've done a lot of interesting design work integrating maps into interfaces, different kinds of visualizations that use mashups of maps and things like that. And they're going to, I think, be giving a kind of a tour through the things they've done and talk about some of the issues and principles that they've discovered in doing that. So that's next week's talk. This week we have Vladlen Koltun, who's on the faculty here at Stanford, and who we have, I should say, recently sort of welcomed to the floor on which the rest of the HCI and graphics people sit. He sort of, over time, moved into this area and is looking at the area of virtual worlds. And it's a sort of different talk. One talk I had here in this series many, many years ago was Jaron Lanier. How many of you have seen Jaron Lanier? Okay, he's the person who popularized the idea of virtual reality, and he's kind of a wild man, right? He's an inspirer of all the things that it could be in the future and sort of psychedelic and all that. And I think that was great for getting the field started. But what's happened over the years is reality has to settle in virtual reality. Mm-hmm. And the question really isn't what is the things you could imagine, but what are the things you can do? The group here, the what's it called, Virtual Worlds Research Group? Or?
Basically my research group, yeah.
Is looking at taking a very concrete sort of computer science look at what makes virtual worlds work. And that's what we're talking about today.
Thank you very much, Terry. That was a great summary of the pragmatic approach that I'm taking to this field. So, by way of background, let me just say that what inspires my work, what has driven my work for the past couple of years and is still driving it, is the potential of computer graphics in particular to enable a richer way for people to communicate at a distance. A richer way for groups of people to interact without having to be in physical proximity. And to sort of drive that notion home, I'd like you to consider what we are doing here right now. Okay? So I'm speaking to you, and you can all hear me speak. You can all see me speak. I can see all of you, and all of you, if you turn your heads, can see each other. We know and we feel that we are situated in the same space. And that is very, very powerful, because any of you right now could raise a hand. And I would see you raising a hand, and I could respond. I could prompt you and ask what your question is. And you could ask the question, and everybody around you would know who is asking the question, where the question is coming from. Everybody else could turn their heads and see who is asking the question. And somebody else could jump in and respond. And we would be able to have a kind of spontaneous, ad hoc, unplanned conversation that we can have when we are situated in a physical space together. And people can walk in and walk out, and we sort of use these physical laws, this physical reality that enables us to hear where sound is coming from, to attribute speech and general communicative signals to particular people, and to use this physical space that connects us in a very intuitive and seamless way that we've evolved over millennia to utilize without even noticing it. Consider another example. Think of a cocktail party where, let's say, about 100 people are together in a large space. And if you walk into such a party, you'll notice that people have self-organized into smaller groups, into subgroups, into conversations that all go on together without, by and large, interfering with one another. Sound falls off with distance, and so small groups of people, even when there are many more people in the same space, small groups of people can organize simply by being near each other and speaking towards each other into distinct conversations. And you could very naturally walk from one conversation to another simply by moving from group to group to group. And groups can self-organize in this way. These are just two examples of the way in which we use physical proximity, the fact that we're all situated in the same three-dimensional space for communication, for very powerful, natural communication, which is the way that we are used to communicating, and which drives, without us even noticing, which underpins education, collaboration, all kinds of applications and contexts where groups of people need to be together and communicate. And my sense is that computer graphics can be instrumental in enabling this kind of natural, seamless communication to occur at a distance, where communication is mediated by computers and networks, so that we could have this very natural experience that I've described, even without being in geographical proximity. That computers and networks could create this kind of experience with this kind of seamlessness, without us having to be in physical proximity. And this is, of course, very powerful, because I could have a meeting like this, I could have a talk like this with people being able to jump in, ask questions, and spontaneous conversations developing. I could have it with any group of people anywhere in the world, as long as they are connected to a network with a powerful enough client, without requiring me to drive to the airport, get into an airplane, and so forth. Now, how would this work? Why is this possible? This is possible because nothing I've described so far, while relying on us being situated in a shared three-dimensional space, nothing I described so far actually requires that I be able to walk to you and touch you. None of this actually requires physicality, in the sense of being able to physically interact. And what this means is that this experience that we're having right now could be mediated by a computer. In principle, with good enough input and output technology, I could be having a very similar experience to this standing at home in front of a large enough computer screen, which would render this environment from my point of view and show all of you to me, and communicate the signals, the communicative signals that I'm generating, right? And this is the idea behind what's traditionally been called networked virtual environments, and is now increasingly called virtual worlds. The idea is that we all participate, we all take part in a computer graphics generated world, in a world that could look very much like this, but would be virtual, would be modeled with geometric models. And each of us would have self-representations. Traditionally, yes?
So on this view, is computer graphics and video conferencing, moral equivalence, and it's purely a question of pragmatics, which is better?
I think there is a much deeper distinction here, actually, and I'll try to touch upon it. So what I would like to describe is this way of doing it, where you have a computer graphics generated world, a computer graphics generated environment, and we all have computer graphics generated self-representations that all participate in these environments, and we view the world through our self-representation, and we communicate through this self-representation, and others perceive this self-representation of mine as if it's me. My communication is coming out of it, other people see it as me, and I see all of yours, I see other people's self-representations, okay? And again, given good enough input and output interfaces and interaction mechanisms, the idea is that this would come close to replicating the experience of actually being together in a shared three-dimensional space. Only this space is simulated. As Scott pointed out, the closest we've come to this, in a sense, so far, is teleconferencing, is video conferencing. But current teleconferencing systems are very restrictive, in the sense that they are largely optimized for small groups of people, well-defined groups of people. So by and large, you need to know who you're speaking with. And what you see is basically a grid of talking heads on the screen. So the entire notion of spatiality, of being able to look somewhere, direct your communication to a particular area in the space, move from conversation to conversation, move across the space, and moreover, engage in activities together. Sort of engage in activities that utilize the fact that you're in a shared space together. Interact with intrinsically three-dimensional objects, like three-dimensional visualizations. That is very severely restricted in current teleconferencing systems. And it could be that some sort of hybrid could evolve. But it does seem to me that the notion, that the way of doing it with a computer graphics generated three-dimensional space and self-representations is just intrinsically more flexible. I mean, it has a lot of expressive power in terms of being able to customize the environment, customize my own representation, and actually it was you, Scott, who told me a few years ago about this paper that became actually one of my favorite papers ever. It's Beyond Being There, right? And the premise behind Beyond Being There is that we should not just try to replicate real-world experiences at a distance, but we should see how we can go beyond them. How mediated, how telecommunication can actually be more powerful than real-world communication. And I believe this decoupling of representation from real-world appearance actually enables a lot of that. Now, all of this, or much of this, is actually not really new. It's not a new idea. These ideas in various forms have been around since the beginning of computer graphics, actually. So Ivan Sutherland, the father of computer graphics, in the mid-60s, went around giving a series of talks called The Ultimate Display, in which he described a vision in which the computer display could in principle present you with a kind of all-encompassing virtual world that you could enter into. He didn't focus very much on communication between different people and other people being in that world with you, but that was in fact when as far as I understand the phrase virtual world was coined by him. And when that movement towards exploring computer graphics generated environment and their function in our lives, beyond just entertainment, beyond just passive consumption of movies and games, but really how they could more pervasively help our lives, that's when it really started. One of the outcomes of that series of talks, which was extremely inspirational and really gave birth to a whole generation of computer graphics researchers, and a lot of people actually switched fields into computer graphics when they heard this. One of the manifestations of this was the virtual reality hype in the 80s and early 90s, which Terry alluded to. And the virtual reality community sort of took literally Ivan Sutherland's vision of immersion and virtual worlds largely overriding our real world senses, but didn't quite pay enough attention perhaps to what one would actually do in these virtual worlds. So a canonical application of virtual reality at that time was, you would don all this esoteric hardware, head-mounted display and optical tracking and everything costing hundreds of thousands of dollars, and then you would be in a virtual room. Well, great, that's a bit like solitary confinement. The experience that virtual reality systems at the time provided, in part because it did not have other people, in part because it did not capture what actually gives life meaning. It's the interaction with other people in our lives. It did not provide a compelling enough experience for virtual reality to really enter the mainstream market for economies of scale to kick in and bring the price of the hardware down. So the virtual reality community is still in this kind of limbo where the community is very attached to full immersion. That's at the center of the vision of virtual reality. And the hardware that enables full immersion is extremely expensive. So the community focuses on very specialized applications whose practitioners can afford the expensive hardware. And there's a kind of spiral that kind of drives itself. Expensive equipment, esoteric applications, expensive equipment, esoteric applications. In parallel, I want to go over this entire history, but in parallel, a much more grassroots movement evolved, starting with MUDs, multi-user dungeons, which were these text-based virtual worlds originating in the late 70s in England and spreading across college campuses all over the world. These were the precursors to current multiplayer games and virtual worlds. And MUDs really brought this idea of communication through alternative worlds and being present in different worlds with other people. Really brought that idea to a lot of people. The United States military did a lot of pioneering research and development into three-dimensional graphical networked virtual environments to enable large-scale war simulations and to bridge thousands and tens of thousands of participants that the military regularly has all around the world participating in these real-time simulations of war scenarios. And virtual worlds were seen as a kind of natural way to bring all these people together in basically a simulated world. There were a number of corporate efforts, and we have the contemporary landscape of massively multiplayer games, virtual worlds, which I will not talk about actually very much. The current state of the field is that there have been a lot of attempts to make this happen. But there are still fundamental problems, there are still fundamental challenges that require a lot of very serious thinking and technical contributions. And the reason I started doing research in this field is that I saw a lot of very deep problems that were being unaddressed. And it seems to me that you can actually list a number of problems. The list is not that long, that if these were solved, we could really communicate in a much more powerful, flexible, rich way at a distance. And the impact could be quite significant. So to me, these problems fall into three general categories. The first is interaction, the second is content, and the third is systems. Roughly, interaction is about interfaces and interaction metaphors that enable us to communicate through virtual worlds and in virtual worlds with the kind of seamlessness that we do in real life, or at least approach this kind of seamlessness where I don't have to think about what I'm doing. It just feels right, right? The second is content creation, is how to actually create these three-dimensional environments and objects to populate these environments with. And the third is system architectures that enable, that support this medium at very large scales. Systems is what I'm not going to talk about today, since this is a seminar focused on interaction, but I will cover interaction and content. Specifically, I will present one vignette from each. One initial research project since I started doing this not so long ago. I will present basically the first project in each of these, and I hope these will be interesting. So first, let me talk about interaction in virtual worlds and how interesting research and interesting technology can make this this interaction more seamless and intuitive. And this is joint work with Sergey Levin, who is a student of mine here at Stanford, and Christian Theobald, who is a postdoc in our department. So if you try using almost any contemporary virtual world system, the very first thing you'll notice is how unlike real-life communication it is. By and large, you communicate with text. You type text, and this text appears to other participants above the head of your virtual representation or somewhere, but you communicate with text. Every single action is explicit, and I'm not just talking about locomotion, you press on arrow keys, but if you want your character to express something non-verbally, any kind of gesture, basically you go to a menu of possible gestures and you look up your gesture and press, and then your character executes this canonical, this standardized gesture. And that is, of course, very, very different from the seamlessness of real-world communication. Now, one part of this is fairly easy to remedy and falls more into system architectures. That's voice. So lifting the limitation of text, this attachment to a keyboard, and enable me to just speak to other participants. That is not very deep interaction research. There are ways to do it. There are some systems that do it. But when you go to voice, you still have the problem that your self-representation doesn't seem to have nonverbal communication, or whatever nonverbal communication it has to be triggered explicitly. And when you go to voice, when you start communicating with voice, the lack of extemporaneous nonverbal communication becomes really, really jarring. Basically, your self-representation starts resembling this kind of zombie-like moving statue with voice coming out of it, but with a very, very, very stilted appearance. So our very first goal was to lift this limitation. Okay, and what I'm going to show you is work that synthesizes body language in real time from speech. So I could speak to other participants, and my avatar, my self-representation will exhibit body language that is appropriate to the speech and is generated on the fly based on what I'm saying. So just to prepare a way for this, let me just cover some previous work in the community that is related. And first piece of work that I'll mention is called BEAT. It's a Behavior Expression Animation Toolkit from Justine Cassel and her colleagues. And what the BEAT work did was create a system that could take text, typed text, and analyze it based on all sorts of linguistics and cognitive psychological rules, break the text down into components, do some simple natural language processing, look up words, see what their meaning is, and generate an appropriate stream of body language for that text. And it could also synthesize speech for the text. And so the speech and body language, after this processing of the text, would be well matched and well coordinated. And this is a good way to endow conversational agents that are not controlled by a human, with appropriate body language. Okay, so if you have an agent in a game or a virtual environment, an autonomous agent, you could feed text into the system, and it would make the agent speak with synthesized speech and generate body language based on all the current understanding in the linguistics community and the cognitive psychology community as to how body language works. Okay. Here's another work from a few years later. It's called Speaking with Hands. So let me just show you some examples.
Ow, dude, you didn't manage to set up your landing.
Okay, so that was body language that was generated for that character. Here's another example.
Whoa, dude, that time you nailed it.
Okay, the work is actually, in a sense, in terms of the approach, similar to the work by Justine Cassel and her colleagues. The difference here is that this body language comes from real people. This body language is actually a real person's body language that was motion captured in a session. And the utterances that the agent can make is limited to the utterances you can compose from sentence fragments by stitching together sentence fragments of what was spoken during a recorded motion capture session. So the application is here is that you have a game, you have, let's say, a snowboard trainer in the game. The snowboard trainer generally talks about snowboarding. So you go to a motion capture studio, record an actor talking a whole bunch about snowboarding. You record their body language. You annotate, you transcribe what the person said, annotate it, tag it in a number of ways, and then you can stitch together. You can basically type in text, and as long as the text is limited to as long as every fragment of that new text has appeared somewhere in the motion capture session, the system will restitch appropriate body language segments from what happened in the session and make the character exhibit that body language. Okay. Now, what I'm going to present is, as far as I know, the first work on real-time synthesis of body language from speech. So there are two interesting distinctions here compared to all previous work on full body language. First, it's real time. Okay, there is no you don't need the text in advance. You don't need to know who is going to speak, what they're going to say, what they're going to talk about. Somebody can come up to a microphone, start speaking in real time, and their character will start undergoing appropriate body language. And the second is, and this is really dictated by the real-time requirement, there is no analysis of the semantics of what's being said, because current natural language processing technology is just not powerful enough to do this kind of analysis in real time with noisy microphone input. So this is driven just by the acoustical properties of the speech. And as far as I know, this is the first, as I said, work on where full body language is generated in real time without pre-processing of the text. So let me just show you what it looks like.
And he looked at me, and I looked at him, and he was quiet. He was very quiet. So anyway, so that's my plane story. Do you have other plane?
Okay, so somebody just came up, spoke into a microphone. We have body language. I'll show a bunch of other examples in a few slides. But let me just talk about how this works. So first, it is based on real body language. Basically, we go into a motion capture studio, and we capture people in conversation. We capture their body language with a motion capture setup, and we capture synchronized speech. Okay? And then we have a training phase where at the end we get a machine learning classifier, a hidden Markov Model classifier that describes correspondences between acoustic properties of speech and body language. Okay? So the motion capture data goes through segmentation phase, clustering phase. The speech goes through a segmentation and discretization phase. And then we have a training process where they are matched together, and we train a hidden Markov model to learn correspondences between speech and motion. It can be multiple speakers, any speakers, and then the hidden Markov model is completely speaker independent. You can have a novel speaker, and in fact, with the results, we do have speakers that did not participate in the training section. Okay, so let me just illustrate each of these stages and talk about them some more. So this is what the motion capture looks like. Okay, he's actually speaking. There's no sound right now. This is Sergey. So we capture people's motions in conversation. This is what the output looks like.
Oh, yeah, actually we went to a South Indian.
Okay, so this is what's actually being captured, and then this motion is processed. So to build this hidden Markov model classifier, we need discrete items on both sides. We need discrete chunks of speech and discrete chunks of body language to learn correspondences. Okay, so the body language is segmented into sub-gestures. Okay, into distinct motions. And this is what they look like. Okay, each is a small motion. Okay, and then to eliminate redundancies and reduce the size of the state space, these small motions are clustered. So similar motions are grouped together into one cluster. And from here on, we only talk about clusters. Okay, and this is basically for performance sake. Speech undergoes its own segmentation process. Okay, speech is segmented into syllables. Syllables are the unit of speech. And for each syllable, we extract discrete parameters that capture the acoustic properties of speech. Now, what are these acoustic properties of speech? Generally, this is called prosody. Okay? Prosody, as opposed to the semantics of speech, as opposed to the content of the text, the meaning of what I'm saying, prosody captures the properties of the signal. So one prosodic property is, for example, pitch, the pitch of my voice. Okay, the higher pitched my voice is, the higher the pitch is. Another is intensity, loudness in decibels, how loud I am speaking. Another is the length of the syllables. You know, am I slurring? Am I not? Now, there's a large body of literature on prosody. And it turns out that prosody, even though it sounds kind of simple, I mean, you just take the waveform and analyze it with various signal theoretic techniques. You don't actually know what's being said. Prosody actually captures a lot of the emotional state of the speaker. It captures the rhythm of speech. It captures emphasis. It captures all those, well, not all, but it captures a lot of subtle and important details about the communication.
So it seems like there's two views one could take. On view A, you say, my body language is completely predicted by what I say. You know, in an information theoretic sense, there's no information gained to prosody. In which case, why bother?
Right.
And in the other case, you say, prosody has all this information that's not present in the speech,
right.
In which case it's impossible.
Right, right. There is a third view, and thankfully there's been a large amount of research into body language and what drives body language. The third view is that it's both, and different kinds of gestures are driven by different aspects of the speech. So let me, since you prompted, thank you, I'll say something about gestures and what body language actually is. So the current understanding of gesture is that gestures, I'll be a little bit simplistic, but gestures generally fall into 4 categories. Okay? There are iconic gestures, deictic gestures, metaphoric gestures, and beat gestures. Okay? Iconic gestures correspond to concrete objects. It's what happens when my hands and my body describe concrete objects or events. So for example, when I talk about a box, or when I say, I just yanked it out of there. Okay? That was an iconic gesture. Okay? Deictic gestures are pointing gestures, and the pointing can be concrete, like when I point to that door, or it can be abstract when I situate reference in space and can then point to these references. So I can say, I met this man, and then there was this woman, and then I can go on talking and say, but then the man. Okay, and I point to the left where I previously situated the man. Okay, that was a deictic gesture. A third type of gesture is metaphoric gesture. Metaphoric gestures capture often fairly subtle, abstract notions that relate to what is being said. So an example of metaphoric gesture, for example, would be if I said, and it went on and on. Okay, and what I just did, the on and on, that was a process metaphoric. Okay, it illustrated that I'm talking about something that goes through time. Okay, the fourth kind is beat gestures. Beat gestures can sort of be simplistically lumped under everything else, okay? Not really everything. It's a distinct category. Beat gesture is this kind of, you could say, hand waving that we go through that keeps space, okay? It keeps space with the speech. It corresponds to the emphasis. It doesn't really have semantic meaning. And beat gestures actually form, just quantitatively, they form the majority of gestures in conversation. Most of the distinct gestures are beat gestures. Now, for beat gestures, there is no argument. They are driven by what prosody is driven by as well. They are driven by the rhythm of the speech, by the emphasis, but they are basically, I mean, it's going to be a little bit simplistic, but they are basically independent from the semantics, from the actual meaning of what's being said. Yes, did you have a question?
Within this typology, do you account for like things like position of gaze, standing versus sitting, motion of body with respect to listeners, that sort of thing?
Not really. In this taxonomy, I was actually just talking about mostly hand gestures and this kind of body language. But yes, there are a lot of subtleties also around gaze, head orientation, and so forth. And there are body motions that are just not gestures, period. Okay, they're not communicative in nature, like scratching my head or something, right? Yes.
Let me go back to Vaughn's question, because I'm not sure, which is the way that people use their body language and gesture is one of the most individuating parts of their personality.
Yes.
Very different for different people. So you do need to train it on the individual, or else it would be somebody else's gestures on my talk.
And indeed, you will see somebody else's gestures. You will see them in the results. So yes, I mean, eventually, one of the goals is to actually learn a space of gestural styles, a space of body language styles where I could place myself and choose my preferred gestural style. And defining these styles and defining this space of styles is actually one of the interesting research issues as well. But for now, what we found out is if we're just, as a very first step, interested in endowing avatars with body language that removes the stiltedness, that just gives them a basic appearance of humanity, so that the illusion of disbelief is not broken every time voice comes out and the body just looks like a statue. Just lifting that just giving them basic plausibility when you communicate. That's the very first step, and we've been to an extent, I think, successful, as you'll see when I show some more results. So going back to your question, iconic gestures form one extreme. Beat gestures form another extreme. Beats can be completely driven by prosody, utterly. Iconics, not at all. Okay, you need to know that it's a box and not a sphere. Okay, but also what's interesting, metaphorics, for example, to an extent can be driven by prosody, and that's a longer discussion that I don't have time to get into. But quite a lot of gestures can be driven by prosody. That's what we found out. Okay. So what parts of prosody you use is important. We basically, so in this little icon, what you can see on top, there is the red waveform. Underneath, there are the pitch contours, what's called the fundamental frequency, and underneath there is the intensity. And we discretize information from these pitch contours and the intensity into a number of binary and trinary features. I won't go into the details, but basically whether the pitch goes to a downward inflection or an upward inflection, whether the intensity is loud, normal, or silent, and so forth. And now we finally get to a stage where we have discrete features on one end, features of speech, and motion segments. Okay, so we know for each motion segment which sort of prosody profile, which set of prosody features it co-occurred with. And we can use this, and this is really the part of the technical heart of the paper, and I won't really go into it. The training process, we can use these correspondences to train a basic hidden Markov model that captures how body language, how these motion segments are driven by prosody and also by their past history, because some segments are much more likely to occur after segment X than after segment Y. Okay, so the hidden Markov model, and I won't go into it too much. It's a basic left-right model where you can think of this evolution of states through time. The big round states are the hidden states. Okay, they are the presumed motion segments. What's going on with the motion? And the little round ones, the V's, are the observed states, which are the speech features. Okay, and the model is trained to basically, given a new speech feature, predict whether the current motion is going to just continue, or whether it's going to be replaced with a new motion, and what that new motion is going to be. Okay, and what goes into this training, these parameters, is how likely one particular motion is to follow another particular motion, given this new set of speech properties, given where the prosody is right now. Okay. The synthesis process, how this model is used in real time to synthesize body language from speech, is actually another very interesting technical component that you can read about in the paper that I won't cover. There's a lot of sort of really cool blending of animation, so it looks smooth, so it looks like a coherent stream of body language, when in fact it's micro motions stitched together. Okay, so let me show you some results.
Some play or some event where the parents were there, and I remember walking out, and one of the mothers hugged me and was like, "I'm so sorry, I'm so sorry," and I was like, "What is going on?" So anyway, so that was a completely different person from the person that the body language belongs to. That was a separate speaker. One interesting thing about this is that this was trained on only 14 minutes of motion data. All of the results I'm showing were trained on only 14 minutes of a person in conversation. Okay, so actually, just the vocabulary of motions that the character can exhibit is very limited. It's limited by only the motions that happen to occur in those 14 minutes. And still, we get we get results that look like body language. They're plausible. And we actually ran experiments. We did a kind of Turing test, basically, on about 90 people, a web-based Turing test, where in random order, we showed 3 motion clips of this, this character with the same 1-minute long speech segment, 3 different body languages. One was the original body language from the mocap session. The other was synthesized body language, was synthesized with our method. And the third was random body language, in the sense that these were motions from the mocap data, but in random order, okay, uncorrelated with the speech. And the results are reported in the paper, but basically we're doing better, much better than random, basically between random and the original one. Yeah.
That's the question. Test data from human authorship recognition using hidden Markov. You can find that you need something like 30,000 characters before statistics can work. You have no way that your statistics converge in any meaningful sense with that little data.
Actually, that depends on the training algorithm. If you use the EM algorithm, that could very well be the case, but we have a custom training algorithm for this data specifically.
Any custom algorithm doesn't put more data in your data if you don't have enough.
Correct, and yet it works.
Proof by assertion.
Well, we can go over this after the talk. Here is another result.
Take you when we're alone. I don't listen to you. When I do listen to you, I sift everything. I bring everything down to reflex response, so I don't really hear you. And the final one, we just took a clip from a movie, from Office Space, and fed it to the system.
It's a problem of motivation, all right? Now if an Initech ships a few extra units, I don't see another dime. So where's the motivation? And here's something else, Bob. I have 8 different bosses right now. So that means that when I make a mistake, I have 8 different people coming by to tell me about it. That's my only real motivation, is not to be hassled. That and the fear of losing my job, but you know, Bob, that'll only make someone work just hard enough not to get fired.
So we are definitely working on improving the system, using more sophisticated machine learning techniques, and also obviously having a richer set of training data that in particular can capture a wider range of emotional states. So for example, if you feed really angry speech into it, it just doesn't look angry enough. That's because we just didn't have much angry training data in the training set. But as a first cut, and as the first work of this kind, it seems to yield plausible results, and the evaluation, the Turing test style evaluation supports it. So yes, Manu.
So have you shown any of this stuff to somebody who directs movies? And what would their reaction be? Because they're used to watching people who with dialogue, and they essentially tell people what body language they should be using.
Yes.
So what would be their reaction to something like that?
I would expect, I have not shown it to movie directions. I have interacted quite a bit with AI practitioners and computer graphics researchers, and also people who work with the movie industry, computer animation, motion capture people. I would expect that a person who directs actors, who directs movies, would have a very negative reaction to this work. First, because the body language just isn't as good as what an actor would generate. Second, in its current form, it takes away the expressivity. An actor would really want to control the body language and the subtleties. And one of the limitations of this work in its current form is that the body language doesn't really convey any more information than what is already present in speech. The body language is generated from speech, so it doesn't convey any richer information. It just sort of plugs this gap. It gives the appearance of humanity. It gives the plausibility, so you can participate. So you can have, you don't have that break in immersion where something looks jarringly off, right? But in the real world, the most widely accepted cognitive theories are that actually we do transmit more information through the body language, and there are experiments that verify that with body language that is mismatched to speech, and sometimes body language can actually override the speech. So one of the next steps that I'm really interested in is a hybrid method where you to an extent sense my real body language and complement it with a synthetic model to produce a stream of body language that I can control, that is much more personalized, and yet is stabilized and made coherent by this underlying probabilistic model of body language.
I was just thinking of a different industry. In gaming, the non-player characters, this seems like something would be just great to use to generate the motions. What's the state now of how much gesture motion they do generate for those characters?
So I have, yes, I have people, unlike people from the movie industry, people from the game industry are really interested in this. Without me ever reaching out to them, they are really interested in this. As far as I understand, this is primarily to control the human-controlled characters, not the agents. For agents, it seems that they are fine with just using motion capture. If you know what the agent is going to say, you can just mocap the body language. But in multiplayer games, for example, where people interact with each other and you see other people's characters and people speak with each other, then you really need something like this, and people from the industry are definitely interested. Yes?
You said that in the Turing test, your method falls somewhere between the random and the
gestures generated by a human being. What metric do you use to see whether your method is good enough, or what metric is it just human, my feeling that it's working good, or is it a concrete metric that you have?
So we asked 3 questions and asked for each of the 3 videos, and the response to each question was rated on a Likert scale, 1 to 5. I don't remember the exact questions. It was something like, how plausible are the movements of this person? How plausible is the body language of this character, rated from very implausible to very plausible on a 1 to 5 scale. And 3 questions like this were asked about each of the 3 videos, which were arranged in random order. Now I should actually specify that we ran 2 surveys on 2 different sets of results. One was with about 50 people, the other was with about 40 people. On one, it was the same speaker. The speech belonged to the same person that the body language came from. It was the person we captured in the training data. And on that, it was arranged basically as you would expect. Random, around, I don't remember the exact numbers. Let's say random around 3, ours around 4, and the original around 5. The second we did where the speech belonged to a different person. The original motion capture data, the clip that showed the original data, belonged to a different person than the one that the training data came from. Okay? On that, we got fairly counterintuitive results, is that ours did better than the original. Okay? On 2 of the 3 questions. On one, you got fairly even. On 2 of the 3 questions, ours was ranked better. Okay, and just by looking at it, it seems that the person that we trained the model on, the person whose motions are generated, are synthesized by our system, was just more expressive, had more compelling body language than the person. Than the person who contributed the data for the evaluation.
So this is if you had Tom Hanks give my lecture where I wrote the talk, he would do better.
Yes, yes. Now we are still, we still want to dig deeper into this and figure out more thoroughly what's going on there.
Just in terms of sort of basic methodology, is there a notion of call it gestural sensitivity or gestural intelligence in the same way that one has spatial abilities that you might want to correct for across, bringing in even gender issues, cross-gender issues. That was a male we saw up there,
yeah.
A male mannequin.
Yeah, so the psychology literature primarily seems to have concentrated on the generation of gestures, how humans generate gesture. The perception of gesture is something that I've been just tremendously interested in and have found very, very little literature on. For example, I have a nagging suspicion that we are fairly liberal in our perception of gesture in allowing for kind of discrepancies, incompatibilities. So if somehow my facial motions are out of whack with my speech a little bit, which is physically impossible, I just wouldn't be able to do it, you would notice right away. If a computer-generated character has incompatible facial motion, you would notice right away. And yet we did just anecdotal studies with just taking one audio segment and placing it on top of a different video segment with the same person, just giving the talk, but saying something entirely different. And the synchrony is off. The rhythm of the speech is off. But if you synchronize it, it is surprising how much of the gestures look fine. You actually ascribe, it seems that we just ascribe meaning to gestures, even if they're different gestures. Okay, so the iconic gestures are clearly mismatched. But with metaphorics, it's like we are very generous in sort of assuming that the body language is appropriate. So the perception of gesture seems actually much more flexible than the generation of gesture. And it's something that I haven't found enough rigorous literature on. And if I have time and willing students, I would actually be into running some experiments myself to see just how far we can go, how much we can err and not violate perceptual boundaries where something feels jarringly wrong.
Is there a small vocabulary of perhaps 10 or 20 words that are particularly gesture prone, like this and that?
There are certainly more gesture prone words with others than others, and one of the sort of interesting questions is, can we actually in real time maybe detect some of these words in a real-time speech stream, right? And that's something we want to look into. So far, we just assume that we can't really, we're not going to look at semantics at all. But one question is, so what semantics could we get in real time with noisy microphone input? For example, this and that. Perhaps we could.
So if you could distinguish between point 1 and point 2, where you'd say point 1, point 2 versus one thing and two things,
right?
You could have quite realistic gestures.
But these are also things that you don't want to get wrong. Okay, these are also very dangerous things, right? You need to be pretty certain before you do this,
So you're a beneficiary of the sort of meaningless of gestures in the way you're interpreting them.
Maybe that's why you have the high score.
Could be, especially with a model that doesn't work at all. So we're nudging towards 1:30, and I have sort of a whole coherent topic. What should we do?
We have till 2.
We have till 2. Okay. Okay. Well, like raise a hand if at any point you're just dying. Yeah. Okay. So interrupt me if you want me to just finish. I'll try to be quick. So the second subject that I want to cover is work on modeling, on creating three-dimensional objects. And the goal here, what we wanted to look at is how can we allow sort of what I call regular people or casual users or end users or mere mortals, whatever you want to call it, to create compelling, custom three-dimensional objects. Okay, I have a three-dimensional object in mind. A motorcycle, a laptop, a television screen. I want to create a three-dimensional model of it. How do I do it? Okay, that's the question. And the goal is to find a way to do this that requires essentially no training or very little training of the user and has very strong expressive powers. Okay. So this is joint work with Jerry Talton, Daniel Gibson, who I'm very pleased to see here in the audience, Ling Yang, and Pat Hanrahan. So just to, if you've never tried to do computer modeling, three-dimensional modeling, on the computer, let me just show you what it looks like. This is what most 3D modeling interfaces look like, and this is actually, as far as traditional modeling interfaces go, this is as good as it gets in terms of usability. Google SketchUp is considered, the benchmark for user-friendly 3D modeling tool. But like all other traditional modeling tools, what you basically need to do is sculpt. Okay, you start with a blank slate, you start from scratch, and then you sculpt the shape that you want to create. Okay, so my motorcycle, my laptop, my television screen, I start with virtual blocks of clay, and then I cobble them together and chisel them into the shape that I want by pushing and pulling vertices and performing various geometric operations. Now I'm not very good at sculpting, and turns out that most of us aren't very good at sculpting. Certainly not to the extent that we could sculpt, a detailed, let's say, human or a Gothic cathedral or whatever it is that you might want to create as a virtual object or a virtual environment in a computer. The vast majority of us are not capable of this kind of creation. This is just closed to us. Now, the modeling problem, the problem that most people can't actually create computer graphics content, three-dimensional content, has been recognized as one of the the central challenges for computer graphics that is preventing the expansion of the medium, because people can't really create in this medium. I mean, if virtual worlds are to become ubiquitous and to become this communication medium that I and a number of other people think that it is capable, that they are capable of being, then in principle, what would really help if it would be as easy to create virtual environments as it is to create web pages and populate them with content. And virtual worlds could provide a similar function, in a sense, to web pages. But in addition to, let's say, disseminating information, they could provide an environment for real-time communication in these environments. Anyway, that was a bit of a digression. So in computer graphics, there's been a number of attempts to ease the modeling process. One idea is to bootstrap sculpting with sketching. Okay, so before you start sculpting in 3D, you outline your shape in 2D, and some geometric algorithms sort of inflate your shape to 3D. So this is the wonderful TEDdy system by Takeo Igarashi, where this is, it's very appropriate, given the algorithms it's using, it's very appropriate for stuffed toys, actually. That's why it's called TEDdy. And so you sketch a stuffed toy, and TEDdy just inflates it into a three-dimensional model. There are some obvious limitations with this. One, it is kind of appropriate for stuffed toys, but you can't imagine sketching a Gothic cathedral in this way. There are certainly very strong limits on expressive power, and follow-up work to this has found that there are very strong limits on the expressive power in this approach. And the second, which might be a peculiarity of mine, I'm not really great at sketching either. I mean, I couldn't draw a decent circle to save my life. And it turns out that really, I mean, we could sketch something approximate, but if I'm thinking about a motorcycle or a laptop or a television screen, I wouldn't really be able to sketch what's in my head. I'll recognize it when I see it. I could maybe customize something to be what I see if I have the right interface, but I wouldn't be able to sketch it. Now, another approach is using computer vision techniques. For example, if you have a video of a real-world object, then there are ways to try to extract a three-dimensional model out of that video, or perhaps a set of images, not necessarily a video. There are limitations with this approach as well. First, again, there are limits on the quality of the objects that are produced. There are often very strong artifacts. There are limits to how you can control the shape and more importantly, the texture of the objects. Often the resolution, the detail in the objects that you get in this way is very restricted. And there is sort of the more fundamental objection that you need a video, an appropriate video or set of images of the object that you want to create in the first place. So let's say I want to model a hummingbird. Well, I need to go out and capture a video of a hummingbird while it doesn't move, okay, in order to get a hummingbird model with this approach. So again, it's pretty amazing technically how far it's been taken, but there are some limitations to this. So the approach that I wanted to explore with my students is an approach that I call design spaces, or navigating in design spaces. And the idea is that what if we had a high-dimensional space that describes an entire domain, okay, an entire domain of three-dimensional objects. Let's say the domain of human shapes, or the domain of trees, or the domain of buildings. Okay, what if we had a good, comprehensive, formal specification of a whole domain of shapes? And what if we had a good way to navigate through this domain? So if I had a shape from this domain in mind, I could actually navigate to it. Okay, through this space, I could actually get to that space. Now, if we had something like this, this basically offloads the modeling work to the creator of the tool, to the specifier of the domain. If I could navigate, to the Milano Duomo, a famous Gothic cathedral, Okay, I don't actually have to sculpt it. I don't have to sketch it. I just have to have my space to contain as one of its points the Milano Duomo, and I need to be able to navigate to it through some interface. Okay, so we can have very detailed, very rich three-dimensional models with this approach. Okay, so what's a design space? So a design space is basically a formal specification of a domain of designs, a domain of possibilities. So here's a very simple illustration: space of human shapes, parameterized by height and weight. Just a two-dimensional space, not that expressive, not very detailed, but for every combination of height and weight, you'll have a set of humans with that height and weight. Okay. And of course, with more and more domains, as we, more and more dimensions, as we get to dozens and hundreds and thousands of dimensions, every point in the space gets more and more specific, until with some number of dimensions, for humans, turns out it's about 100, 200 dimensions. You get to a point where every point is very specific, and you can say, okay, I captured the variability in human shapes. Okay, I can really navigate through this domain, and every human shape I can see around me, you know, I'm very likely to find that shape in this domain, as long as it's, let's say, a fully formed, you know, human, standard human. Okay. How do we create these design spaces? There are two sides of the coin, right? Creating these design spaces and navigating these design spaces. First, the creation part. There are a few ways. One way is to just manually specify the dimensions of variability. Okay? And this can be done with trees, for example. So we used a wonderful work by Weber and Penn, who basically went over tree encyclopedias and tree guides and botanical manuals and tried to extract, you know, every single way in which trees differ from each other. Okay? And just list them. They came out with about 100, okay? 100 dimensions that specify all the ways in which trees differ from each other. This certainly doesn't capture all trees, okay? There are some trees that are not, that cannot be specified with this vector, in this parameterization. But it's pretty good, as you'll see if we have time, okay? So these are dimensions like, you know, the width of the trunk, the speed with which the trunk narrows towards the top, the flare of the trunk at the bottom, the curvature of the branches, the number of branches, the number of levels of branches, the angles at which the branches branch out, and so on and so forth, the colors, and so on and so forth. About 100 dimensions overall. So that's one way, you know, fairly brute force, labor-intensive manual specification. Another way is sort of more technologically sophisticated, data-driven, automatic way, which is to just scan a whole bunch of instances from the domain. So this can be done with human shapes. You can put, in this case, about 250 humans into a 3D scanner, get about 250 different human models, and then register them together and use machine learning techniques to learn all the dimensions in which these shapes vary from each other. And then you can use dimensionality reduction to get down to, in this case, I believe it's about 130 dimensions that account for most of the almost all of the variability that you see between all these 250 human shapes. And surely, you know, I think you'll believe me when I say that with a sufficient number of humans and a sufficient number of dimensions, you can really capture the variability in standard human shapes. Okay, so that's another way to create these design spaces. So there are interesting design spaces out there. Okay. Now, how do we navigate these high-dimensional spaces? Again, there are a few approaches. One approach, fairly straightforward, is to just change every individual dimension. Okay, so every dimension, every parameter has a value, and you can adjust that value. Okay, so for example, this is the editor of material properties from 3D Studio Max, where you can see that you can just individually adjust, you know, the ambient component, the diffuse component, the specular component, and so on and so forth. Okay, now, It's simple and intuitive, but there are very strong limitations as to how far you can get. First, you're always limited to adjusting one component at a time. And often to get from one region of the space to another, to get from what you have right now to where you want to go, you need to change a large number of parameters. Let's say you need to change 30 parameters. And none of the single parameters gets you anywhere perceptually closer to where you want to get. Okay, so you want to get from motorcycle number 1 to motorcycle number 2. And by changing individual parameters, it's often not clear whether you're going closer or farther to your goal. You really need to change a number of parameters in concert to really get closer perceptually to where you're going. So often it's just not obvious at all. That would be an understatement. Not obvious how to get where you want to go through this interface. And another limitation is that often these parameters are counterintuitive. Often they are not as nice as ambient, specular, and diffuse. For example, with the human body shape space, the parameters were just automatically extracted by principal component analysis, and some of them have just very counterintuitive, subtle global effects on the shape where it's not clear at all what the parameter is doing. Okay. So, second approach to navigating high-dimensional spaces is to just flatten them. So embed them onto a two-dimensional space. This is an illustration of a space of musical styles that was embedded into 2 dimensions. You could present it in high dimensions, but you could just flatten it and create a 2-dimensional map, a map of the space, and then you can just move around this map. Okay. Again, it's intuitive. It's good. It utilizes metaphors that we're used to, the map. But it is very limiting. I mean, it throws out all the dimensions but 2. So, your high dimensional design spaces is basically gone. All the expressivity, all the content that was there, you just extracted a 2-dimensional manifold. So you really now have a 2-dimensional design space. And I won't go into the mathematics, but this is a really big deal. There is much more room and much more expressive power in a 100-dimensional space than in a 2-dimensional space. Okay, you can just pack much more there. I mean, yeah, you can have a bijection between a 100-dimensional space and a 2-dimensional space, but that's not that's not really the point here. You can really express much more and much more intuitively with a high-dimensional space if you could just navigate it. So a static map, has some disadvantages. There's been other work in the computer graphics and HCI community into exploring these high-dimensional parametric spaces. One work is design galleries by Joe Marks that suggested different ways to present alternatives, basically nearby alternatives to where you are, kind of discrete snapshots from the space that are near where you are right now, and then you could choose an alternative, and then it would present you a new set of alternatives. Okay, so we kind of wanted to do something a little bit different. We wanted to find a way to combine the advantages of maps and the advantages of design galleries. So without some of the disadvantages. Okay. So the approach that we took is basically to have an interactive map, a map that is not a static embedding, but an interactive map that looks and feels kind of like Google Maps. Okay, so let me show you what I mean. This is a prototype tool that we did for trees that Daniel worked very hard on. So let me show you how this one tool for trees looks. Okay, so you always have a fully formed tree in front of you on the left, fully detailed. On the right, you have this interactive, what feels like a map of the space of trees where hopefully similar trees are near each other. So, you have the fir trees here, the evergreens there, the palms there, the cacti are there. And it's zoomable and pannable, okay? So If you zoom out, you can get sort of a global overview of the space, see where you want to go. I want a cactus. OK, I'll zoom towards the cactuses. You get a finer and finer variation. And then you can sort of guide yourself to, to your mental image of what it is that you want. OK, that's if it works. We're just on our way there. Sure.
Biologists know, this is a northern plane, southern plane, eastern, western, Eurasian, whatever.
What did you?
Instead of just a random, more or less random artificial world, we have real Earth, with real trees.
Google Earth.
Google Earth, if you wish.
Okay.
Why not use that because biologists or whatever, the experts that study the Earth and climate and trees and whatever, have a sense where these things are.
So if I want to create a tree, how would I create it in this interface?
It's up to you what Earth you want. If you want to recreate, it's obviously not unique, is the point. I understand. But there are some samples.
So you mean if I want
Earth or think of Venus or whatever.
I see.
You have trees. Though.
I see. So you mean, say, if I want to create an eucalyptus, and I know that eucalypti grow in a particular region, I can go to that region and sort of find a eucalyptus. Yeah. That's an interesting idea.
Because most people have a sense of what the world looks like. In your world, I wouldn't find I'll happen like furs. I had no clue where to look for the furs in the world.
Well, that just means we.
But I know I in the mountains somewhere, I probably will likely find the furs I like.
Okay.
Just a suggestion.
Along those lines, have you tried integrating this with search? Like, can people label oak tree or something like that?
That's the obvious next step. In this tool that we released over a year ago, we did not have time at the time to integrate search and tagging, but obviously it should be done. Semantic labeling, search, absolutely.
So can I go back one slide? Because you're projecting your 100-dimensional space onto 2 dimensions there.
Yes.
What's the principle by which you do that projection?
Okay, that is the technical heart of the work. Okay, because this is not a static map. That is sort of one of the big contributions, that basically every time you move or zoom into a new area, it samples new points from the high-dimensional space itself and then creates a custom embedding for your current view. Okay, so every time you move, it just extracts a new 2-dimensional manifold from the part of the space that you're interested in. So you're never restricted to one single static embedding. Now, where does it sample it from? Okay, so here I need to digress a little bit and explain sort of the biggest challenge and sort of an opportunity also for technical contribution for this kind of work. And the biggest challenge is that when you have an expressive enough space and a high-dimensional enough space, most of the space, in fact, an overwhelming part of the space is just bad. It is not models that you would want to look at. So by way of illustration, you can consider here on this simple 2-dimensional space, a 1 foot tall, 200-pound human. Okay, and as you add dimensions, it just gets worse and worse. So for example, here are random points, okay, from our space of humans. Okay, these are not particularly bad. They're just randomly sampled humans from the space. Okay, and here just randomly sampled, again, representative, typical points from the space of trees. Again, if you think about it, this is what you would expect. If you have 100-something parameters and you set each value just randomly, uncorrelated with all the others, you would kind of expect to get something nonsensical.
We'll likely find those in the ocean.
Yeah, I haven't shown you the bad trees. These are just the normal trees. The bad trees are much worse. So a lot of the technical details are in the paper, but basically, the reason our sampling works and this whole nice sort of iterative maps and embedding things on, embedding regions of space on the fly, while always, trying to present the most appealing, the most parts of the space, create the two-dimensional sort of snapshot of the region you're looking at that is most likely to be what you want. What's driving it is this technique called adaptive kernel density estimation, and adapting this technique to high dimensions, making it work with the kind of performance we need, and being able to do the kind of sampling, the local sampling, constrained sampling that we need to do from it. That forms the much of the technical contribution, and I won't go over it in this talk. But basically, what this technique does is it allows you to go from a set of points, just a discrete set of landmarks in the space, to a continuous distribution over the entire space, a probability distribution that basically tries to tell you how good any point in the space is likely to be, given the assumption that the landmarks you gave to it are good. Okay, so in a nutshell, the tool works by aggregating all the trees that all users of the tool have ever saved, interpreting these as just noisy votes for points in the space. If somebody bothered to save it for themselves, it might be good. Okay, there are some security issues that we can talk about. But basically, we aggregate votes from all users of the tool. The votes come sort of as a side effect of users' self-interested activity. Then we use adaptive kernel density estimation to get a continuous probability distribution on the space that we can sample and generate these maps, these iterative local snapshots of the space for every user. Okay, so to test whether this thing works, whether it's good, we built this prototype tool, we launched it a bit over a year ago. We kept it up for a year for download. It was used, not just downloaded, but actually used by, I think, over 17,000 people from over 130 countries in this time. And together they created over 6,000 trees. And what happened is we launched it with only 20 landmarks. We just put 20 points in the space. And over time, the maps that the tool was displaying of the space got richer and richer. It was showing more and more regions of the space, and it felt like the users were collectively just kind of exploring this space and mapping out clusters of interesting trees there. And these are some of the things they created. They look, almost all of them look very, very different from the 20 trees we just seeded the database with. But that's only part of the picture. The main result, or what I'm most proud of, is this. These are the times it took our users to create these models. The times were collected anonymously, completely in the wild. We don't know who these people are. It's just that all the tools send anonymous data, usage data, to our server. Okay, and you see models that would have normally taken days, if not weeks, for professional modelers to create. Created by novices in minutes, and we ran user studies, and over 80% of the users of the tool reported that they are novices when it comes to 3D modeling. They are not fluent in it or expert in it. No, all of this, these are just over 20 minutes, so we don't report creation times. The times were, by the way, from the moment that user very first opened the tool for the very first time to the time the tree was saved. So, I mean, in the modeling world, times like 3 minutes for that are just absolutely unheard of.
To it, and then let some experts loose in this set of what the crowd thinks is good. What sort of interaction? I mean, this is. Good here means interesting from a design point of view versus from a pure representational point of view.
This is a great question. You could, for example, seed it with experts and let the experts kind of nudge the community towards what they think is good, or you can give greater weights to points contributed by experts, or you could tag them as these are the experts' landmarks. Yeah, and have the map generation prioritize those. Joel was first.
So it's very clear that you can quickly produce something that looks like a tree, and that's great. Do you have a sense for how much people are able to produce the thing that's in their mind's eye? Because that was what you initially pitched the idea as.
Yes, that was my initial goal, and we're not there yet. The current incarnation of our tool does not do as good a job at it as I would like it to. And part of what's missing is actually search. Is the fact that you currently don't have semantics on the trees, and that the embedding is also, with all the mathematical firepower we put into it, without knowing the semantics, it just doesn't produce maps that are as semantically coherent as I would like. It does sometimes put a fir tree next to a palm, okay? And what you would like is just a really nice something that behaves like a map, yet doesn't restrict you to a single two-dimensional subspace. So we're not there yet, and we are very interested in making it more powerful so that you could actually go from a mental image in a few minutes to a fully formed three-dimensional model. But we're not there yet. Actually, there were a couple of... Yes, Jeff.
Oh, yes, sure. I have a highly speculative question. I'm just curious, if you want to foster people's exploration of this larger design space, do you have any thoughts on how the environment or context in which the tree is rendered might actually shape the modeling decisions people are making?
Oh, that's a great question. Offhand, I have no idea. We just put them, as you saw, on a little hill and a little sort of meadow. But yeah.
Put them on Google Earth.
Great, we could put them on Google Earth.
Nature.
Yeah, that's a great question. Bjorn?
Yeah, I just had a quick follow-up to Joel's question, and that is, maybe since you already have that underlying your tool is a parametric model of the design space, to what extent it may just be the right solution to go back and forth, to have a hybrid working style where you enable exploration through browsing, as in your technique, and then at some point when I need to narrow the disparity between what I have in my mind's eye and what's currently on the screen, then I just flip to expose all the dimensions explicitly. And yes, the exploration is now slower, but all the semantics are right in front of me.
Yes, that is exactly what we do, in fact. So yes, we have two modes. I didn't dwell on that, and thank you for bringing that up. It was in the video, but it was kind of, I didn't touch upon it at all. We have two modes, actually. So one mode is what I did dwell on, and that's the exploration. There's a button that flips that panel and gives you all the dimensions and tries to give them as descriptive names as possible. And we did some analysis on the user logs that our server collected from all the users, and we want to do a more thorough, comprehensive analysis of it, but just from largely anecdotal just examination, people go back and forth and do exactly what you said. They have sort of high-level orienting yourself to a general area first, and then they can fine-tune. For example, if I want this tree that I currently see on the screen, but I want it not purple but green, okay, the easiest possible thing to do is to just flip, change the color to green, because I know that. Okay, and people go back and forth. And in the questionnaires, we asked people, how useful the two modes were, and it seems that people, like both modes. Although the questionnaires weren't as rigorous as I would like them to be in our next work.
Okay, thank you.
Thank you very much, Terry.
For more, please visit us at stanford.edu.